Welcome, inspectors, to this pre-job briefing explainer. Today, we're diving straight into NDT Control in welding. Look, non-destructive testing is arguably the single most critical quality control activity in fabrication. We are going to break down exactly how we evaluate weld quality, all without destroying the material itself. This explainer is designed to sharpen your diagnostic skills and keep your technical edge razor sharp. All right, here's our standard operating procedure for today. We're going to cover the high stakes in oil and gas, identify those hidden defects, figure out how to choose the right NDT method, go over material limits, and wrap it all up by breaking down the complete inspection workflow.
So let's kick things off with Section 1, the absolute high stakes in oil and gas.
As quality control inspectors, our main goal is ensuring pressure boundary integrity, right? We're operating in these crazy high-stakes environments, like oil and gas, power plants, petrochemical facilities, where literally one bad weld can lead to an absolute disaster. In these sectors, deploying techniques like radiography and ultrasonics, they're the only thing standing between a long, safe equipment lifespan and a complete catastrophe. We're not just out there looking for a pretty surface finish. We are verifying the fundamental safety of the entire system.
Moving right along to Section 2, identifying hidden weld defects.
Because before we can even think about deploying our testing methods, we really need to know what our enemy looks like. What kinds of dangerous flaws are just lurking inside that weld metal, waiting to compromise the joint? A beautiful surface weld can hide a multitude of scents. Our actual job, it's to see right through that metal. Let's start with the absolute worst offender out there, cracks. These are, without a doubt, the most critical defect you're ever going to encounter. Why? Well, because they act like a sudden failure time bomb. While other defects might just cause a slow leak, a crack creates this massive stress concentration point that can just propagate instantly under pressure. Boom, total failure, with zero warning. So finding a crack is always priority number one. Then, of course, we have slag inclusions. These guys act like imposters, hiding right inside the weld metal. During the actual welding process, non-metallic impurities, think flux or oxidation, can actually get trapped as that molten pool solidifies, and they silently weaken the connection from the inside out. Because, let's face it, where there is slag, there is no solid metal.
But hey, the lineup of usual suspects definitely doesn't end there. You might run into porosity, which is basically trapped gas pockets, turning your internal weld into Swiss cheese. There's lack of fusion or lack of penetration, or the metal just completely fails to bond or reach the root. Or, you might see undercutting carving these weak little grooves into the base material, maybe some internal laminations, or even literal holes caused by burn-through.
All right, that brings us to Section 3, choosing the right NDT method. Because we definitely don't just pick a diagnostic method out of a hat, we actually matrix our 4 major tools: visual, magnetic particle, radiographic, and ultrasonic testing, against the exact flaws they're meant to find. Got a surface defect? You pull one specific tool from the kit. Suspected deep internal flaw? Well, then you need a totally different approach. For instance, if we think there are internal flaws, like those slag inclusions or porosity we talked about, radiographic testing, or RT, is an absolutely incredible tool. It uses X-rays or gamma rays to give us a permanent physical or digital record of the inside of that weld. It's literally a medical X-ray, but for steel. But it does carry a pretty heavy logistical burden. We're talking strict radiation safety perimeters, clearing the whole area of personnel, and definitely higher operational costs. Alternatively, ultrasonic testing, or UT, is another total powerhouse for internal defects. It sends high-frequency sound waves that literally bounce back when they hit a discontinuity, like a crack. It gives you incredible deep penetration and immediate results, completely avoiding the radiation hazards of RT. But what's the catch? Well, it's the human element. UT requires a highly skilled, specialized maestro to actually interpret those waveforms accurately. Next up is Section 4, material limits in testing. Now, the really crucial point here is knowing the jurisdiction of your tools, because the metallurgy strictly dictates our choices. Take magnetic particle testing, or MNT. It is phenomenal for finding surface discontinuities, right? But it comes with a massive limitation. It only works on ferromagnetic materials, like carbon steel. If you're working with non-ferrous materials or stainless steel, MNT is completely useless. You literally cannot magnetize them. So for those stainless steel and non-ferrous jobs where MT totally fails, visual testing, or VT, takes center stage. But truthfully, VT is always your first and most important inspection, regardless of the material type. Long before you ever bring out the X-rays or sound waves, your eyes, maybe aided by gauges or borescopes, are establishing the baseline. You're checking the weld size, the profile, and looking for surface cracks. It is the absolute bedrock of quality control.
All right, let's jump into our final section, Section 5, the complete inspection workflow. So now that we know our diagnostic tools and the material limits, how does this actually play out in the field? A really common misconception is that NDT only happens after the welder turns off their torch. But in reality, Stage 1 is way before welding, verifying your materials and joint prep. Stage 2 is during welding, where you're monitoring fit-up and preheat temps. Stage 3 is after welding. That's when you deploy your VT, RT, or UT. And finally, Stage 4 happens after post-weld heat treatment, requiring final inspections and hardness testing should just make sure the heating process didn't accidentally degrade the metal.
And listen, throughout this entire active timeline, we're never just making subjective guesses. Every single dimension measured, every single indication found, has to be strictly weighed against recognized acceptance criteria. Whether you're building a pressure vessel under ASME Section 8, some structural steel under AWSD 1.1, or pipelines under API standards, these codes are the law. They define exactly what is perfectly acceptable and what absolutely must be rejected. This workflow is basically the ultimate path from a raw joint to total confidence. It's a really rigorous 6-phase system. Phase 1, the weld finishes and your visual inspection begins. Phase 2, you select the right NDT method based on the material and whatever defects you suspect. Phase 3, you execute the test. Phase 4, evaluate the results against the code. Phase 5, accurately record and report everything. And finally, Phase 6, making that heavy responsibility decision to either officially accept it or send it back for repair to maintain integrity.
As we wrap up this explainer, I really want you to internalize this. Your mastery of these techniques is literally the only thing standing between pressure, boundary integrity, and a totally catastrophic failure in the field. So you've got to ask yourself, the next time you sign your name to that final report, are you absolutely certain nothing is hiding beneath the surface? Keep learning, keep inspecting, and I will see you in the next explainer.